Okay, well, Patrick Michel, who is somewhere sitting, where are you, Patrick? Okay, in any event, he brought to our attention a little problem that we have, and it was somewhat inadvertent, and so we want to correct that. And basically, that is that the students were basically required to pay for their attending the banquet. That's a fairly expensive little item for a student, and so we want to fix that problem. So we are going to have, number one, students who have presented papers or have done a poster paper are invited to attend the banquet at no cost this evening. And second, and secondly, if in fact you did pay for that dinner, we will refund that. And so again, we apologize for that. This conference has been a little different on the standpoint of the finances, and so, but I think we're in good enough shape to be able to make sure we do that. So again, I think that's good. Anything you want to add to that?
Yeah, and those students who now intend to come to the banquet and did not register before, they should go to the reception desk, to the registration desk, and register now for the banquet. Again, for them it will be free.
Yeah. So that's good. And just as a quick count, how many of you fit our students and will be coming to the banquet tonight? Oh, I'm sorry? If it's really, I think this is the normal price for them. Again, if you presented a paper or gave a poster, we can cover those. Okay. And so I guess, and again, if you want to do that, register, and if you need a refund, you should talk to the desk as well. Now we just go for Lindley.
Okay, so now we continue with the normal program. So we will start now with session 7 on disaster response, and the presentations will be chaired by Lindley Johnson and Barbara Jennings. And I believe we have one presentation will not be given.
Yeah, that's right. We've had one person that has dropped out, so this may turn out to be the shortest session that we have here, which in some ways is good since it's before lunch, but unfortunately, this was a session that the original idea was an opportunity for emergency response community to talk with us a little bit about how they saw the asteroid impact problem in planning and response disaster preparedness. And although there was certainly some interest from that community in participating in the United States, of course that's the Federal Emergency Management Agency, wanted to participate and had originally made some plans to be here, but with the transition in government and such in the U.S., when it came time to commit to it, they had to, felt they couldn't commit at that time. So we had to do a little bit of scrambling. They actually were going to chair this session, so we did a little bit of scrambling, and Barbara Jennings and I stepped up to host this session. So I think we've got 2 or 3 good talks here, though, about some of the emergency exercises, asteroid impact emergency exercises that we've had with the emergency response community, both in the United States and in Europe. So it'll be some interesting talks. But first, we have Mark Boslough from Sandia Labs, which is going to talk to us a little bit about the things to be considered for emergency response. Now, let me say a few words about Mark. He's, as indicated in the last session, has been doing this kind of modeling and looking at this problem for quite a while. I can't remember if you were in the first PDC we had in 2004 or not, but you were certainly been involved with this all along, and the only other person I can think that around that has been doing this kind of modeling effort is maybe Galen. But what you saw in the last session with all the work and modeling that has gone on is kind of the legacy that Mark has given us in getting the interest in this area for determining what the impact effects are and what we might have to deal with. So we have Mark to thank a lot for how this area has grown in the community and gone beyond just as astronomers speculating what might happen if it impacted. So Mark, take it away.
Thank you for the nice introduction, Lindley. This is kind of my go-to opening slide. This is my Tunguska simulation that really changed the way I think about that event and convinced me that it's more dangerous than people had previously thought. By the way, I want to mention my co-author, L.A. Lewis, who is at FEMA, and as people probably know, things are going on in Washington, D.C. right now, and he's been very distracted by that and was unable to come. I offered to fill this slot, but if he had presented this talk, I'm sure he would have had a very different focus. So in previous, before I started running these airburst simulations, people kind of just assumed that at the altitude of peak energy deposition, you could set off a static point charge and estimate the damage on the ground. It turns out, at least in the case of Tunguska, you get a lot more damage on the ground if you source the energy there, but allow put the momentum, allow it to maintain its velocity so that the momentum carries it downward with a total conservation of energy. You get a stronger shock wave at the surface, and you do still get that butterfly pattern. Now, if this happens over a city or a populated area, it's not trees that get blown down, it's windows that get blown in, as we saw 4 years ago at Chelyabinsk. So I'm glad that that Donovan gave the previous talk, because what I'm attempting to do is sort of a crude version of what Donovan and Lorian have been doing with these ensemble risk calculations. But I have a particular focus in mind, and what I am looking at, the goal of this is to see whether you can have a significant savings of lives just by bringing back awareness of the old duck and cover exercise, the ones that people my age used to do when we were kids. If you see a flash in the sky, you don't go to the windows and look out, you do the opposite. You go and you dive under your desk, and it could take a couple minutes for the blast wave to get there. Now, I haven't confirmed this, but according to Wikipedia, there was a case in Chelyabinsk where a teacher had her students do that. None of the students were injured. The teacher went to the window to look, and the teacher was seriously hurt by flying glass. So if that I don't know if that's true, but it is in Wikipedia, and it should be confirmable. So my idea really is to do estimates where I assume people will be injured at a certain rate, and we can actually use Chelyabinsk as one data point, and run ensemble airburst simulations, plot the wind fields, convert to damage zones, compare. What I also did is compared hydrocode to simulator results from the Purdue simulator, which is sort of my quick and dirty way of quickly trying to do estimates, sort of order of magnitude type estimates, and then sum over probability weighted areas, and then test the sensitivity to assumptions. So that's basically all I'm doing here. And what I want to do is kind of show graphically how this works. So here is a set of simulations for different entry angles. And I did this very much the way I did that Tunguska simulation. This was the projection on the ground. These are wind speed contours. So you can see, an almost vertical impact is roughly circular. It looks more like the bullseye. Whereas as you get to shallower and shallow, more oblique impacts, it starts to look more like a butterfly with wings. It's coming from above in these simulations. But these are not all of equal probability. There's this sine to theta dependence. So if you scale the area of these as sine to theta, well, 45 degrees is the most likely. 85 degrees of this is the least likely. I didn't do a 5 degree because it gets really difficult to do the really shallow ones. And so if you're looking at effects, well, you'd kind of sum over something like this. just to account for entry angle. I did 8 megatons, roughly 50-meter asteroid. This is my Tunguska size, 4 megatons. This is 2 megatons. These are a bit under-resolved. I'm not concerned with the exact distribution of the contours. I'm more interested in the areas. So as we get down to the smaller and smaller ones, they start to look a little pixelated, and they start to look more like Space Invaders and slices of toast and things like that. So now let's just look at the 45-degree one. This is a comparison in size and intensity. I clip it above the absolute, complete, and utter devastation zone. So these are the relative sizes of the various contours. But if you now weight it by probability, and I used Al Harris's table, which I have a version of in my own spreadsheet for this population. The biggest one ends up being the little one, and you're summing over these. When you sum over probability, you can sort of show that graphically as areas. And so now I do a very crude, quick and dirty estimate of casualties, and I define 3 zones, as we've done in the past. So this ranges from the very outer, the outer zone is where glass windows just begin to shatter, up to where all this stuff happens, and the next one, that boundary starts here and goes to here, and this boundary starts here and goes to here. So basically everybody in here, they don't have a chance. I mean, even if they shelter in place, they don't really have a chance. Here, duck and cover is probably pretty effective. Here, it might be hit and miss. It depends kind of where you are. Remember, this is also the outer ring, so the people here have the most warning. The people here, their houses are getting blown down, you know, they may or may not have time to get down into the basement. So, and I'm kind of thinking about zero warning events like Chelyabinsk, like Tunguska. There was no warning. The first warning was the flash of light. So now I can just create some assumptions. We can disagree with these. What I'm thinking about really is a tool where you could even create an online tool where people can manipulate a slider and say, well, shelter in place, might reduce fatalities from 20% to 5%, or whatever numbers you want to put in. And you can test sensitivity that way. So here are the Purdue simulator results, the same kind of thing, only using the Purdue simulator. And here they are scaled by probability, again, area by probability. And you can see there's a heck of a lot more yellow than there is any other color. And if you assume random population density, most people are going to live in the yellow. So if duck and cover saves lives, you're saving a lot of lives in the yellow zone. And here's kind of a composite. So here's the relative area of all of those added up. Using those assumptions that I listed, 10% die unsheltered, 1% die sheltered in the yellow zone, we get this level of fatalities unsheltered and this level of fatalities sheltered. I'm not saying that that's what the numbers are. I'm just saying this is an example. So here's my comparison of the simulator to my hydrocode simulations. These are the damage zones. And here's Tunguska, and here's the actual Tunguska for comparison, which is actually fairly similar in shape and size. And here's the simulator, which shows nothing for these small ones, but the hydrocode shows that there actually is a significant area of damage, and this would be the Chelyabinsk, although I didn't run it at the same altitude. And the actual Chelyabinsk damage zone was much, much bigger. This is from Popova et al. So now we do probability weighted area on that, and I'll just go through those really fast. Okay, so this is now, I can compare this to what Donovan showed. I have a complementary cumulative probability density function for size. Now this is what we presented a couple of years ago at the IEEE aerospace conference, and with Al Harris's latest numbers. Now, Al has said this conference that this tail is actually now even lower. So this is the deaths per impact curve that I lifted out of the 2003 Science Definition Team report. So you multiply this by this is now smaller. I get a number that's actually very similar to Donovan's. To me, if you're within a factor of 2 or 3 on something like this, you're doing pretty darn good. But where we really differ is in how these are partitioned between the big ones and the small ones. And I think the small ones are a lot more dangerous than what Donovan and his group are saying. So the bottom line is I'm convinced that shelter in place would save a significant number of lives. If we really want to do that quantitatively, we can do this. We can do a better job on this. It would be great to collaborate with Donovan and his group on this because I think they already have the machinery to do this. The exact number depends on assumptions. It would be nice to have a tool to dial those assumptions in, and one way to do that would be an online tool, so anybody can do that. Policymakers, emergency management people can do that. And my time is up and my slides are up, so I'll take questions. Thank you.
Okay, well, Clark's got his hand up, so let's see if we got guess I'll give him mine. I don't know if we got guys with mics or not.
Yeah, shelter in place and duck and cover was something that in the half a century ago, possibility of nuclear war was really on a lot of people's minds, and you could have a program like that.
That's right.
You can't possibly get everyone ducking and cover for the extremely rare case of asteroid impact. Now, people do shelter in place due to other kinds of hazards, and possibly you can marry it to people where they run for when warned of an earthquake happening in 10 seconds. I don't know, but what about people running to the windows?
Running to the windows for if they see, okay, so if you see a bright flash
I'm talking
in the
about
sky,
education
okay.
of
So,
people.
and this really is a matter of awareness and education. People need to know that if there is an extremely bright flash in the sky, brighter than the sun, it's dangerous. Don't run to the window and look at it. It could be an asteroid. It could be a nuclear explosion. Either case, you do the same thing. You go away from the window, you get in the interior part of the house. That's duck and cover. Duck and cover is not synonymous with shelter in place, though. It's one form of shelter in place.
The principal ignorance that needs to be corrected here is very, very simple, and that is just that people understand, unlike seeing a flash of lightning and then listening for the thunder is going to come a couple minutes later. And so people, I think the reason the damage was so great, injuries are so great in Chelyabinsk, was people thought that after a minute or two, all danger was gone and they might as well go out and enjoy the contrail in the sky. And all you really have to do is educate them that that's not so.
Any other questions over here or anyone? Okay, thanks, Mark.
Okay,
Appreciate it.
thank you.
Okay, our next presentation on the schedule is the one that dropped out. So now we'll have a presentation by Detlef Koschny of the European Space Agency, runs the Space Situational Awareness NEO program there. I look on Detlef as kind of our counterpart in Europe for running our program. So Detlef.
Yeah, thank you very much, Lindley. So I'm going to be talking about impact threat exercises and in particular where we stand in Europe with our interface to the emergency response agencies. And to sort of preempt my own discussion, we have something in place already which is called NEO Information Plan, It should really be called NEO, Information Dissemination Plan or something, but that was already too long. So that's the word we use for a document which defines the interface between the European Space Agency and our member countries in the case of an imminent asteroid impact threat. And it defines something called impact warning, which is what we would give out in the case of this simulated PDC 2017 impactor. It also defines something called information release, which is much more vague and much weaker, where we realize that in case there is an event like the recent flyby of a really bright object, or even just a fireball entry somewhere over Sri Lanka, which turns out to be a piece of space debris, that also there we have to be proactive and informing our counterparts in the countries. Now, our counterparts are the emergency response agencies in the European countries. This document defines for both of these happenings, the impact warning and the information release, we have a procedure on what we actually need to do with respect to them. And it defines criteria for when we actually should distribute the information. So, you know, the 1% in 50 years or something like that. It defines which information should be distributed and also to whom do we actually distribute it. And the content of this document was based on 2 workshops that we did and a lot of personal interaction with different players in Europe. And I just wanted to give you a bit the background and what the main points from me as a space agency representative were, that the information that I get from the emergency response people. So this is the process, how we went through it. And I do want to mention the lower left box where I want to say thank you to Lindley. The initial version of the information plan was written by Gerhard Drolzagen, whom you saw doing some announcements before. And Lindley got us started with providing information. So thank you very much for that. And of course, what we did is we looked at similar threat scenarios, earthquakes, avalanches. We had a discussion in our group here, and I think it's important to realize that your typical preferred threat scenario that you want to compare something to depends on where you live. For example, in Germany, I'm from Bavaria, we have a problem with flooding. So very often the Danube decides that there's too much rain and then you have problems. And you have to evacuate people. There's nothing special in doing that. People know what to do. It's just a completely different case. In Switzerland, the first thing they told me when I went there is avalanches. That's their threat scenario that everybody is aware of and also knows what to do, and they train people in that case. So I think one of the messages we got is that, you know, these emergency response agencies, they know very well what to do in different scenarios. And when I first presented the asteroid impact threat in Switzerland, they told me, oh yeah, but I showed them videos of Chelyabinsk, and they had an expert there who looked at the videos and said, oh yeah, this is an overpressure of blah blah hectopascal. It turns out was exactly what Peter Brown also deduced from the impact, just by looking at the YouTube videos. And he saw, oh yeah, windows shatter. And just 2 weeks before I was there, they had a simulated scenario with the inhabitants of Zurich, the capital of Switzerland, where they simulated a gas tank explosion. And it's the same thing. So it's not that they don't know what they're doing. And I think we spent maybe sometimes too much time of trying to say they don't know what they should be doing. We just have to stick from a space agency point of view, at least, to providing the factual information. So this is what we did with analysis of similar threat scenarios, and we had a first workshop with just 2 participants, Germany and Switzerland. Both of them are now participating. So where's the camera? Hello, Deutsche Weltraumlagezentrum. Hallo, Nationale Alarmzentrale in Zürich. Grüezi miteinander. So I'm happy that they can remotely participate, and we had some input from them. So they did a first workshop. We worked on this information plan document. We presented it to our program board, which is the highest level political board in our space situational awareness program, where the near-Earth objects are part of. And we had a second workshop where now other people came in from the member countries because they saw that it worked well with 2 countries and they wanted to provide their own input. And that resulted in the final document, which was approved last year by this program board. So we now have a procedure in place which is basically endorsed by the political representatives to us. Now we just need to implement it, and this is our agenda now for the next 3 years. So some summary of the first workshop, and I realized I already presented that because it just happened before the last Planetary Defense Conference in Frascati. So there is a paper there where you see some details. In a nutshell, what we did is we did sort of a super simplified version of the scenario that Paul has prepared for the previous and for this PDC. And you see my level of simulation. I took a Google Earth screenshot and a PowerPoint red ellipse, and I simulated it. I think it took me about 1/1000th of the time that Paul spent on that. But it's also only 1/1000th of the quality, but it was good enough to trigger some discussion. And I think that's this part we discussed before. We need to educate people. We need to educate the emergency response agencies. So what we did is we always did sessions of 2 hours where we presented to them, okay, it's 5 years before and this is what we know. And then we were discussing the following things. What information do you as emergency response agency think you want to have from us? What would you actually do with it? What would you expect us to be doing, us as space agency? And whom should we actually give the information? And how will the public respond was always something we asked them, because they know much better than we as space agency how the public responds to a threat. So the main results were, well, I said this before, we have to provide factual information. It should be timely, it should be reliable. And I think with all these fake news discussions, I think there is a difference whether Mr. John Smith puts something on the web page or whether NASA or JAXA or the European Space Agency puts something on the web page. So because we are trusted and we have to make sure that it stays that way. I think that's really the important message. Interestingly enough, they all said we want to be informed already when there is a low probability. And in the end, we agreed to 1% impact probability up to 50 years in advance, which happened to be the numbers that we also agreed on in I1 and same page discussions. And of course, that's not a coincidence. They don't do anything with that. They will not immediately send out messages to the public, but they want to know, just to be informed. The regular information now daily when you're really close, like shortly before the impact, is needed to build the trust. Information on impact effects was requested. Now that was something where in our initial program we were not really asked to work on all these impact effects. It was felt it's enough if we tell them, okay, there's these numbers 1, 2, 3, 4 PSI, which don't mean anything to me. That should be good enough for them. Well, even when I gave them hectopascals, this expert knew, but the emergency response agencies much prefer what you showed in your last graph with like wooden structures fall down, and that's the kind of language that you need. So we are also now starting with more energy on really working on an engineering impact effects tool. Okay, for high-risk threat, 24/7 availability was requested. We should provide background information on NEOs. That means train the people before, which is something we're doing now, also by them participating in this scenario. The second workshop, we had not all member countries participating, but a few more, so that's good. And just also for the first one and for the second one, we have an external public report. If you want that, just contact me. I was always meant to put it somewhere on a website, but probably the easiest is that you just send me an email. So there we now had all of Europe affected. So how do I keep the people excited? Well, the asteroid happened to break apart. Does that sound familiar? And so I had one impact over Finland and Norway and one in Spain and things like that. So the objective there was now to establish a clear decision-making and communication process. So we really wanted to finalize our information plan. And there we agreed on these numbers. There's some duplication here because I simply copied this from the report. One point was we had a long discussion. Do you need to have a daily update or something? And basically the key message there was what they normally do is they provide information when there's new information, and then they say, okay, we do not expect any new information before, say, next week Monday, because then we'll have radar observations or something like that. So you don't need to say something every hour if there's no new information. Well, we had this before. ESA should provide information on the expected ground damage. So the key point, and this came also as a feedback from the Swiss colleagues that participate in this scenario, they said what they would want at this stage of the PDC 2017 scenario is the third bullet from the bottom, information on the impact probability, the location, potential damage zones, always with uncertainties. So they always say plan for the worst, hope for the best. So they want the uncertainties. This is, at the same time, the message said, okay, this is already in our information plan, so they are fine, they don't expect more. The German colleagues were basically sending a message yesterday where they said no action, so it's still too early in this scenario for them to really do something. One thing which we shouldn't forget, they also want information after the actual impact. So like, where was it? Can you really confirm that this is the size? So we are not out once this thing has impacted. So what we are doing right now is we are implementing the actual mechanism. The German Weltraumlagezentrum has a situational center, you know, where they inform their customers, which are the local emergency response agencies, but also the German military. In certain areas on this planet, what's going on in terms of space weather. They send out collision warnings of satellites, and we are now implementing something like a close flyby information thing on their website where we directly provide the information to them. We are defining these information sheets, which we think is a good idea to have, that you have like for a close flyby like 2017 GM, you put all the interesting information on a nice sheet of paper, which can also be used by journalists and so forth. This is something which is just available in draft. We'll finalize it after the workshop here because some of the people that actually came up with this are in the room. And then the next steps are that we expand then first to Switzerland and to the other countries. So that's where we stand. Thank you very much. I think that's all.
Okay, question up here in the middle.
Detlef, what happens if the impact is predicted in a zone where it's not Europe, somewhere else? Does all the mechanisms, I mean, ESA could still make predictions, but all these mechanisms that are only applicable for Europe, the agencies, don't. So what happens?
Yeah, we asked our Swiss colleague exactly that. Now he's sleeping right now, so we'll know in 4 hours. So ask me that question later today. What I do know is I was asking that question when I was in Switzerland visiting their place, and they showed me that they were actively following, for example, the Fukushima incident. And they had all the information available, and of course all these emergency response agencies, it's like us, they talk to each other, they have the conferences, they're not working in isolation. So yes, they would also follow this, like the PDC 2017 event, even if it's not predicted to happen over Switzerland or Germany or some other European country.
And another small question, do you think actively in ESA about plans for mitigation missions? I mean, this would be the second step. Is there another branch of activities?
Yeah, this is what you heard on Monday from our Director General, that of course, as you're well aware, we tried very hard to get the asteroid impact mission off the ground. That's now definitely not going to happen with the 2020 launch, but it's still on DG's agenda. So this is definitely something we're
No, I
following.
don't mean that. I mean, in case of an impact in Europe or somewhere else on the planet, would ESA develop and make proposals for mitigation missions for the real threat?
I'm not really sure what you mean. I mean, what we are doing every day is we are participating in the work of, for example, SamePage, where you saw a presentation from our colleagues of Flight Dynamics, for example, where they analyze many, many mitigation mission scenarios. Is that what you're after? So
No,
the answer
I
is
think
yes, we are doing that.
Okay, and we can discuss offline later.
Okay.
Okay, any other questions? We have some time. There's one over here.
Just one quick comment. I think it might be useful to compare the TC3 case as it happened with all the trying to notify airlines or pilots to look for the impact with what we would have wished had actually happened also from the standpoint of the meteoritics science people collecting the material as a way to learn more about this kind of kiloton scale impacts. Because these are quite frequent and might actually prove a valuable exercise also regarding communication to states or disaster management agencies in countries outside the European zone in this example.
Yeah, this falls under this information part where we don't really have a serious impact, but maybe just a fireball predicted. What happened, of course, for TC3 was that a Dutch amateur astronomer heard about it, and he is the one that works in the Dutch Meteorological Institute, and his job is to inform KLM pilots about the weather situation. And he told one of the KLM pilots, look, if you're flying over Sudan, look in that direction, you will see a fireball. And they actually confirmed, so they have a visual observation of the fireball. And I talked to the pilot afterwards. He was 2 months before retirement when it happened. And he said that was the best thing that ever happened to him in his whole career. And he really wants ESA and the Dutch Weather Service to do this more often.
It's a good thing he wasn't closer.
Okay.
One more question, Dave.
Yeah, it's more of a comment. I think that working with the disaster agencies is great. I'm really quite worried about saying we should have a public campaign such as Mark suggested. The obvious questions that you might be able to answer is, when's the last time someone was killed by an impact? When was the last impact that killed anybody? How many people get killed every year? I think the answers are disappointing if you want to get people excited.
I think the Hollywood movies, though, have done that for us to get them excited. I think it's just a matter of giving them more.
There is a statement then maybe that I should make. That was also an important message I got. When I gave my first presentation, I was saying these things. 1 million people will be killed, or 10 people will be killed. And they said, Detlef, don't say that, because if we as emergency response agencies do our job right, nobody will get killed. So that's why now in all our work, we convert it immediately just to damage in terms of millions of euros.
Yep. Okay. Yeah. Thanks, Detlef. One of Detlef's slides there reminded me of the first exercise I had with some of the other government agencies back in 2008. But we've gotten more sophisticated on our exercises since 2008, and so we have the diabolical Paul Chodas here, who's been involved in helping us increase the fidelity of that exercise work. And you see the quality of presentation we have at like this PDC. We have had 3 exercises now with our Federal Emergency Management in the U.S. Paul is instrumental in helping us put those together, and I also want to mention that Paul has now taken over as the director of the newly renamed and enhanced Center for NEO Studies at the Jet Propulsion Laboratory, and is doing a fantastic job there. Paul?
Thank you, Lindley. I'm using the same background for the title slide as in the PDC. I hope that, though, you can switch your heads to a different scenario. And so what I hope to do here is just talk about the scenario that we carried out last year and point out some of the similarities and some of the differences to the one that we're running this week. And there were a few good points to learn from that. I want to acknowledge my extensive co-authors, Mark Boslough, Bill Ayler, Paul Miller, Megan Brooks-Ayal, Donovan, Matthias, and Lorian Wheeler. They all are the same kind of group that you've seen in action this week as well. And we did this all last October in Los Angeles. So this was the third in a series of NASA and FEMA tabletop exercises that we've carried out. And I have to say that the first one, we had an impact in, I believe it was Pasadena, Maryland. It was somewhere near DC. The second one, and I think Lindley had something to do with this, we were going to have an impact somewhere around Houston. And in fact, there's a city called Pasadena there. So the third one had to be Pasadena in California. So this is you're seeing a theme here, but we're having a little fun with it. But it is an entirely different situation with different locations across the U.S. This was an opportunity for teams to learn how to cooperate with each other and how to communicate, what to communicate back and forth, what NASA could tell FEMA and vice versa. And we wanted to identify information gaps in what we wanted to understand, what FEMA wanted to know, and FEMA wanted to understand what we could give them. The exercises, the exercises I mentioned in 2013 and 2014 were held at FEMA headquarters, and this was the first one that was held remotely in Los Angeles. The final point here, and I don't know whether Lindley has already mentioned this, the lessons learned were used to inform the national strategy for NEO impact threat preparedness, and there is a document that came out of this exercise, so we actually had a product. Okay, so now we're back to exercise only, and there were a number of injects. We carried this out over really just one day, so we couldn't have too many injects. But still, I tried to divide it up and to talk about different stages in a scenario where you would know different amounts of information. This asteroid, 2016 TTX, another three-letter acronym that's impossible for a real asteroid. It was discovered on October 1st of 2016, and we did the usual. It reached 1% impact probability on the day of the meeting. We computed the range of possible orbits, and as usual, the impact probability starts very small and it grows quickly as you take observations. This one was different because it was in an Otten orbit, 295-day orbital period. So it's an orbit that's interior to the Earth largely, 100 to 300 meters in size. It was the impact probability, as I said, started very low, 0.02, went up to 0.1, and then 1%, which is the threshold that Detlef mentioned. So a question that we would get from FEMA folks, and it's something that we would try to explain to them, is why don't we know right away whether an asteroid will impact? And I think that many of us, find that we understand the situation of orbital uncertainties, but the lay people did not. So that my answer to that in 2 points was just to say, even though orbital motion is very predictable, the telescopic observations aren't perfect. And so you don't know exactly where the asteroid is, and you especially don't know the velocities. And when you project ahead to a potential impact point, as you know, you get large uncertainties. So here's the orbit that we picked for this one. It's inside the Earth's orbit, which is the outer circle. And the usual discovery was here. And there were many revs and then a possible impact point. So again, I zeroed in on the possible impact point here. And there's a very familiar diagram following a theme here with a large uncertainty region at the moment that the Earth crosses the asteroid orbit. So we know when the Earth would cross the orbit. We simply don't know where the asteroid will be at that instant of time. Risk corridor, you're very familiar with that one now. So this one crossed the United States because this was an American exercise. But as usual, it wrapped around the world. Rotating frame diagrams. I did not show this to the FEMA folks because it is a little confusing. But to this audience, I think you may understand it better. So the Earth is fixed in this frame, and the Earth-Sun line is fixed. So this simply asks the question, where is the asteroid as a function of, in this rotating frame, as a function of time? And in this case, it was discovered here. It took a loop, and it went in front of the Earth as we go around the Sun, and it was in a kind of a resonance, and it came back to impact 4 years later. So the warning time here was 4 years, which is not enough time to mitigate. So the second inject was after the second apparition. You would actually get more observations. 3 months have passed, and suddenly the impact probability goes to 65%. That's the same kind of thing we've had this week. But then again, there would be no further updates for a period of time. So you're stuck with this uncertainty for 5 months with, you don't really know whether it's going to hit or not. Although this was a pretty high impact probability, I have to say. No deflection mission, there wasn't enough time. A characterization mission, however, such as the one we're considering this week, and we've already done, was introduced in this scenario, and there was time for that. So it would be very fast, and fast flyby. You've seen this sort of thing before, where the uncertainty region, now these are snapshots in time, as the Earth in a geocentric frame crosses the asteroid orbit, it intercepts the uncertainty region, and you can see the gravitational focusing. Each point is modeled separately. And this is the moment where they start to intersect the Earth. So the risk corridor for this one, as you saw, initially wraps around the world, and Lorian and Donovan did their usual worst-case analysis of taking the Monte Carlo points and considering what kind of damage would be around each of these points. So yellow represents the minor, green significant, and red the total devastation potential. But again, a long risk corridor. Next inject was about a year after discovery. So now the impact probability is 100% because we've observed the asteroid yet again, and now we have observed it for over a year, and that means we know its orbital period really well. It's tracked extensively. The impact footprint is now in Southern California, but again, it's now kind of on the other side of the sun, so it's no longer in view. So once again, we know it's somewhere in Southern California, but we don't know where, and we have no updates for 2 years. Very difficult in this scenario. The size, by the way, is, as usual, very uncertain. You need the characterization mission to understand the size, and we've done that again this week, and so but we have done this once before last year for this exercise. It's really important. So this was the impact footprint of that exercise, quite large. There was part of it in water, part of it over land, and part of it over an urban area. Lorian and Donovan did this worst case analysis with the upper bound on the size of the asteroid, which was about 300 meters, I believe. And now we're seeing a very significant area of potential complete devastation over a wide region. The characterization mission, by the way, is fairly easy in this case because the orbit of this asteroid is convenient. So we actually developed a characterization mission profile. This is a little bit later in the scenario when the impact ellipse is shrinking, but now it's shrinking over Los Angeles here. The Lawrence Livermore folks, I think you heard this earlier from Suhail, analyzed flood heights from this was the lower end, 120 meter object, and they were looking at the inundation that they would get from an impact just off of Malibu, and their conclusion was that we would see flood heights up to 1.5 feet. And the inundation could extend 100 to 250 meters inland, so they did very extensive simulations here. I'll go rapidly through these here. At the extreme end, 300-meter object, the flood heights could be much larger, but only 3 feet I was surprised it was that low, so this is an interesting result, if the impact was just off of Malibu. And back to Donovan and Lorian's analyses. This was I guess this was, at the 1 year point in the scenario, we had this usual casualty range histogram with 10% of no casualties, but 1,000 to 10,000 casualties had a very significant chance at that range. Now I have to advance quickly through the scenario. As we got more observations and the spacecraft arrived at the asteroid, suddenly we know the size of the asteroid. And in this case, it was smaller, on the small end, 120 meters or so. So that was good news because there was no chance of mitigation of this asteroid. Okay, so I'm happy to say it was on the small end. So the question then is, how accurately would we know the location of the impacts? And of course, if you have a characterization mission, you're able to compute the impact location that much more accurately. So that's the second advantage of the characterization mission. I did a footprint that zeroed in at this level over Los Angeles, which extend Los Angeles, the urban area, covers the whole graph here. So we know, in this case, that even 6 months to impact, we would know that a footprint that is comparable in size to the city. And then, in the end game, 2 days to impact, we would have radar. And in fact, that is also possible in the 2017 PDC exercise. We will have radar as well. But radar in our case is not as needed for the 2017 case because we have had a rendezvous spacecraft there monitoring our asteroid. And so the radar is not going to add more positional information because we already know it well. In this case, we just had a flyby mission to the 2016 TTX. So radar added a little bit of orbital information, and it would start about 20 days before impact. Now we're able to pinpoint the impact location. It was near Pasadena, just south of the Rose Bowl, in fact, which is very near JPL, I'm sorry to say. Yeah, so we're equal opportunity impact location people here. And the radar would also confirm the size of the object because you'd actually be able to image the object. That was the final footprint. The worst case impact effects that Mark Boslough computed for us had this sort of size. Now this was, I believe, a 300-meter size. So we're flipping back and forth between worst case and the actual case later on in the scenario. In any case, total devastation within 40 kilometers of the ground zero was, I believe, the result there. So let me just end by saying what the final circumstances are. I think Detlef mentioned that you want to also have a kind of a wrap-up and talk about what actually happened. These are the numbers: 55 megatons. This is the entry velocity of 13 kilometers per second. Larger airburst than Tunguska for a 120-meter object, obviously. Crater-forming impact was possible but not certain, which I find fascinating, but that's a result from Mark Boslough. Without evacuation, and because we're landing in an urban area, the number of casualties could certainly run into the millions. But with evacuation, hopefully much less than this. Someone asked, and I'm putting this in a red box, what are the chances of this? This is an awfully scary scenario. But if you run the numbers, the actual chances of something like this happening in an urban area like Los Angeles are extremely small. So 1 in 100 million is my guess at the rough back of the envelope estimate of the possibility of this scenario actually happening. In any area or in Los Angeles? In this specific area. In any area the size of Los Angeles. Yeah. It's a big difference, yes. Yeah. In an urban area, yes, that's correct. That is what that number is. Yes, wait for the mic and you can ask that question. I'm done. Thank you very much.
Oh, okay. I was going to say. You let Paul finish his presentation before we hit him with the question. Okay, questions. And here's one up over here.
So you discussed what you said to the FEMA folks, and I was curious, what kind of feedback did they give to you? Is there anything that they said to you that our group wouldn't have necessarily had the background to know
Yes,
a thing?
and thank you for asking. I forgot to mention that point, and Lindley can add to it. First of all, they were shocked at the size of the potential damage. They were amazed at the warning time, in this case, would be years, perhaps 3 years. And it's something that we're not at all familiar with. Now, we had involvement from the state officials, emergency management officials. There was questions on how this would be handled politically, whether there would be appeals to the federal government for preparation. There was consideration and discussion of the evacuation time frame, and also discussion of the evacuation, of the believability, in fact, of our predictions, and whether a certain fraction of people would refuse to evacuate. So there is a report that came out of this that summarized some of these results. I don't know, Lindley, would you care to add to that?
Yeah. The report is just about to be published on the web, so you can look for that through our Planetary Defense Coordination Office website. And it's a very different thing for the emergency managers to handle, to know that you're going to have a disaster 3 years from now.
Yeah.
It's, it just boggles their mind that, they have that much time to think about it. But so other factors, as was being talked about down here, and previously David mentioned and such, have to be dealt with by society in that case. Romana, up here in the corner.
Well, it's actually more of a comment than a question, because now we heard about the national preparedness plans, or the probabilities, and then Detlef talked about the regional information dissemination within ESA and ESA member states. But what happens at the global level to the countries that don't have the capabilities, where to receive information? So I just wanted to point out these recommendations for international response to neo threat that's provided for establishment of I1 and same page also had the third part, which talked about disaster preparedness, and actually talked about an international advisory group on disaster preparedness, and also linked this advisory group to one of our programs, which is called UN Spider, UN Platform for Disaster Risk Reduction and Emergency Response, that has the mandate basically to connect the space community with emergency agencies, and does technical advisory missions in countries that really don't have the knowledge or access to technologies or their own satellites and so forth. So, I think this is still the area that it's work in progress, and we were talking about, that it would be really good that when UN Spider does technical advisory missions, there should be a NEO module there to raise awareness, particularly in the countries that are not involved in such endeavors, and also not participating here in the Planetary Defense Conference, for example. And also to look at some examples, like, for example, at the global level, like a tsunami warning system that's been set up by the International Oceanographic Commission of UNESCO, for example. So that could also be built upon. Thanks.
Thank you.
Okay, questions down here still? Here's Phil over here.
Paul, this is really interesting. It brings up this whole question of, that might describe as, living in a dangerous world, and how does one live in that world? And to some extent, I think the issues of how one lives with earthquakes or with tsunamis are actually a good example, because we have a warning system in place in some areas. For example, sirens are one example of that. Emergency broadcasts are another example. And so, this might be something which maybe is already part of this community, but just thinking about how to both educate, has been mentioned, as well as put in place mechanisms that the public has some comfort level of, okay, if there is an earthquake, we have ways of dealing with this. If there's a tsunami coming, we can warn you and tell you to, and just so that you live in this world as we learn how to take control of this world. Sort of a stopgap measure in a sense.
Both of those events are much more common and familiar to the public than the event we're dealing with here. And so we can certainly put information out.
Well, you're going to hear this afternoon a little bit more about how those things are being thought about and what we're doing. Okay. So anybody else want to stand between us and lunch? Oh, there he is. So we're to the brave person right over here.
Very short. What do you do if the impact more short time before impact?
Much shorter time?
The shorter time, yes. What main etaps in this case?
Things would happen much more rapidly.
Yes, yes.
But however, we would identify the impact spot also much more rapidly. We've had the TC3 case when we had a small asteroid coming and discovered only 20 hours before impact, and that was a very busy day. So we have a feeling for the time frame, and we would be able to get a very small footprint. In that case, it was a very small footprint 12 hours before impact, for example. That's an example of what could be done. Hopefully we would find it farther out than one day. But, and in fact, if it was a larger object, we certainly would find it much farther out than one day. So fortunately, the more hazardous objects will have a little bit more warning, but it's still a difficult situation.
Thank you.
Okay. Well, with that, I think...
Oh,
2 or 3 seconds. Table 3.3 of the
1001,
2003 report, in
1002.
fact, has that quantitatively spelled out. It's something like 2% of events of that size would kill 1 million people or so, and the frequency of that happening is about once in 1 million years rather than 100. But you're not far off.
An order of magnitude here or there, what the heck. Okay, lunch. Do you have any announcements before lunch? Lunch. Lunch is called.